Hi everyone, this video resumes in Chapter 8 in Section 8.3, the section titled Strengths of Acids and Bases. Let's get started. Acids and bases are classified as strong or weak depending on whether they react completely or partly to form hydrogen ions or hydroxide ions. There's really no sharp distinction between a weak and a strong acid. It basically just depends on how completely they dissociate to form these two ions. Like I said, there's no real sharp distinction. The only thing is that some compounds, like for example hydrochloric acid, react so completely that everyone else is considered weak. So it's sort of like a relationship. Everyone's based off of the most strongest ones because those are the ones that produce hydrogen or hydroxide ions so strongly and so easily that everyone else is considered a weak acid or a weak base. This is table 8.1. I want you to be able to recognize the strong bases and strong acids. They're common. You should have seen them and been familiar with them already from general chemistry, so it shouldn't be that difficult. Like I said, they completely dissociate, and one thing that you're going to notice is that the equilibrium constants are very, very large. We're going to be working a lot with equilibrium constants like I mentioned before, so you'll notice that these constants are super large compared to the weak acids and or weak bases. So now let's talk about weak acids. Weak acids all react with water to donate a proton to water. For example, you have your hypothetical weak acid HA, you've got water. That weak acid is going to donate a proton to water and leave the weak base ion behind, just like a typical strong base would do. And if I wanted to find the equilibrium constant, or in this case we're going to call it the acid dissociation constant, we would write it like that. So it's nothing new, it's nothing that you've never seen before, it's products over reactants. Except now we're calling it the acid dissociation constant. Weak bases, it's the same story, except now the weak base is grabbing a proton from water. So you've got your B plus your water, and that's going to grab a proton, it's going to become that weak conjugate acid, BH+, and then you're going to be left with a hydroxide. If I want to know the equilibrium constant, or in this case, called the base hydrolysis constant, that's how I would write it. Remembering that we don't include water because it's a pure liquid. So now we know the constants for weak bases and weak acids, and their names for them, the acid dissociation and the base hydrolysis. You're going to have to start recognizing functional groups that make weak acids and weak bases. Carboxylic acids, for example. So here I'm showing you acetic acid and its conjugate base pair, acetate ion, and the acid dissociation constant for it. And just in case you didn't know what the functional group of a carboxylic acid looks like, there it is. It's a COOH. R, remember, just means a remaining group in the molecule. And of course, the representative ion of the carboxylic acid is called the carboxylate anion. Typical weak bases are amines. An example of that is methylamine. It's a very typical weak base, and you see here methylamine. It's going to grab a proton from water, and it's going to become the methyl ammonium ion. And of course, I'm giving you the base hydrolysis constant for that. With amines, you can have primary, secondary, or tertiary amines. So you have your RNH2, which is a primary amine because it only has one remaining group attached to it, and then of course that makes a primary ammonium ion. You have your secondary amine, which has two remaining groups attached to the nitrogen, and that of course makes a secondary ammonium ion, and of course the same thing for the tertiary. Realize that these weak bases, when they become their anions or their conjugate base pair, they're still considered weak. So weak bases make weak acids, and the same concept goes for weak acids make weak bases when they convert to their conjugate pair. So as a summary, don't forget, here I'm showing you the two different reactions, one for weak acid, one for a weak base, remembering that HA is the weak acid, but also BH plus from the base hydrolysis constant is a weak acid, considered a weak acid as well, because that's the conjugate base pair of this weak base. And then the two bases that you have are your A minus, that's made in the Ka, in the acid dissociation reaction, and also your B from your base hydrolysis. So we're going to use these a lot, so get familiar with these symbols and know your conjugate base pairs and don't get confused by them. There's a really important relationship that exists between your Ka and your Kb. And this relationship will help you when you do problems in the future. If you took your Ka reaction, which is up here, and your base Kb reaction, which is down here, and you added those reactions up and canceled everything that you needed to cancel, for example, you can cancel those two HAs and you can cancel those two A minuses, you're left with what? You're left with the reaction for water. That tells you that if you add two reactions, a weak acid and its conjugate weak base reaction together, all you're really left with is the equilibrium constant for water. So that's a very important relationship to know. So Kw is actually equal to Ka times Kb. Because remember, when we add reactions together, we're actually multiplying together their equilibrium constants. So as an example, let's try that. Let's find the value for Kb if we know that the Ka for acetic acid is 1.75 times 10 to the negative 5. So since I know the relationship between the Ka and Kb, it's related to the equilibrium constant of water, I'm going to say 1.0 times 10 to the negative 14th is equal to Ka times Kb. I want to solve for Kb, so just divide by Ka. That's of course the number that I've given you there, 1.75 times 10 to the negative 5. You divide those two numbers, you're going to get 5.7 times 10 to the negative 10th. So that is base hydrolysis constant for the acetate ion. Very simple. Another quick question, which is a stronger acid, A or B? And then I'm giving you dichloroacetic acid with its Ka and chloroacetic acid with its Ka. Remember what I said at the beginning of the video. Strong acids have very large Kas. So that should tell you that the larger the Ka value, the stronger the acid is. So right now you're comparing these two, and obviously it's going to be dichloroacetic acid that's stronger. It's a stronger acid because it has a higher Ka. And it says write the Ka equation for each. We can just go ahead and do it for one of them. Let's do it for dichloroacetic acid because it's the same process. So you would write down this formula, Cl2HCCOOH, and it's in equilibrium with its conjugate base. So you would put the double-headed arrow, and as a product would be its conjugate base, so the dichloroacetate ion, anion, plus that H plus that it gave off. And that's what they mean by writing the Ka equation. So you can go ahead and do it for the chloroacetic acid on your own. So this is something we've talked about already, the pH of acids and bases, but let's remember. So what would be the pH of 0.010 molar hydrobromic acid? You would take the negative log of H plus, so that means obviously the negative log of 0.010, and you put that into your calculator, you should get 2. Is 2 a reasonable pH for hydrobromic acid? Yes, it is. The reason I did this slide is so that you can remember to ask yourself that question. Is the answer that you get reasonable for what you know you should get? Yes, hydrobromic acid is a very strong acid. Your pH should be a very low number. Okay, what about this? Find the pH for 4.2 times 10 to the negative 3 molar perchloric acid. So you go ahead and put negative log of 4.2 times 10 to the negative 3, you get 2.38. First of all, is that reasonable? Yes, it is. Perchloric acid is a very strong acid. You should get a really low pH. Same thing we just did. Now, do you guys remember how many sig figs you should report? Remember that however many sig figs you have in your number, that's how many sig figs you should have in your mantissa. So since there's 2 sig figs here, your answer should have been 2.38. Okay, what about this? The pH of a strong base. What is the pH of 4.2 times 10 to the negative 3 molar potassium hydroxide.
Baby girl. Hi, my little girl. Can I get my calculator, my little girl? Oh, I know.
If you take the pH of that, you'll see that you get 2.38. Now, is that answer reasonable? Of course it's not. It's a base. So that means it should be higher than 7. So what's wrong here? What we did is we forgot to realize that this is the hydroxide concentration, not the H plus concentration. So you have to actually use your equilibrium constant, Kw, to figure out what the hydroxide concentration of this is. So you go ahead and put 1.0 times 10 to the negative 14th and divide it by the concentration of hydroxide ions, which is what they gave you, and you should get 2.38 times 10 to the negative 12. Now, that's what you put in. That's the concentration of your hydrogen ions. So that's what you put into your pH equation. And if you do, you get 11.62. Is that reasonable? Absolutely. So, like I said, you have to make sure that the answer that you get when you do these things is reasonable. So let's try one more. What about the pH of 4.2 times 10 to the negative 9 molar KOH? So now we know, obviously, that we're going to have to convert that into H plus. And when we do that, it ends up being 2.38 times 10 to the negative 6 molar. If you put that into your pH equation, take the log of it, negative log of it, you'll get 5.62. Is that reasonable? Absolutely not, right? KOH is a base, so it has to be higher than 7. So, and you did the process correctly. So what is the difference here? What's the problem? The problem is that look at the concentration that they actually told you KOH is, or the hydroxide ions is. It's 10 to the negative 9. How much is the concentration of hydroxide ions in pure water? Well, from the equilibrium constant, we know, from the water equilibrium constant, we know that it's 10 to the negative 7th. So pure water actually has more concentration of hydroxide and H plus ions than this solution. So there's no way that if you put this solution into pure water, it's going to make it less than what pure water has, if that makes any sense. So when that happens and you know that you've done your process correctly, what we say is that it's really close to 7. The pH is really close to 7 because obviously the concentration of OH ions in this solution is way more dilute than the concentration of hydroxide ions in pure water, or the concentration of H plus ions in pure water. So make sure that you understand that. All right, let's move on. The last thing I want to talk about is some tools for dealing with weak acids and weak bases. Just like we use pH, we can say that the pK or the pKa is the negative log of whatever equilibrium constant. If you don't know this already, whenever you put a p in front of a value, that basically tells you that they're taking the log of it. So that's what the p actually means. So pKa is going to be the negative log of your acid dissociation constant. pKb is going to be the negative log of your base hydrolysis constant. And there's nothing different here. We're just taking the negative log of it. So if you have your Ka at 10 to the negative 4, to get your pKa, you just take the log of that, so it would be 4. Same concept for another weaker acid. If you have the weaker acid Ka at 10 to the negative 8th, your pKa is going to be 8. Regardless of the fact that you take your pKa of these two compounds, realize that they're still classified as weak acids. Don't think that now that you have your pKa at 4, it kind of looks like your pH scale. No, this is not the pH scale, okay? This is just a pKa. We're taking the negative log of this Ka. But it has nothing to do with the fact that now these are becoming strong acids. Absolutely not. We're just taking the log of that acid dissociation constant or of the base hydrolysis constant. You guys are going to have to get familiar with using Appendix B. Appendix B has all of the acid dissociation constants that you're going to need for any problem that I give you. Realize that each compound is shown in its fully protonated form. So for example, methylamine, which you know is CH3NH2, you're not going to look for it as CH3NH2. You're going to look for it as CH3NH3+, which is, again, its ionic form. It's the fully protonated form of methylamine. And the value that they give you of that Ka, and that value that they give you, that 2.3 times 10 to the negative 11th, is really for the ionic form. So do not make that mistake. So how would you find the Kb from methylamine? Well, very simply, you know the relationship now, the equilibrium constant of water, so you would use that to find the Kb of methylamine. Make sure that you know how to find these. Make sure that you could do these problems and you could find them in the appendix, and that you don't get confused. Because I'm gonna give you one of these in the test, and I'm gonna give you a list. You're gonna have to know how to use that list. So for acids that have many different protons that can actually come off, or in other words, polyprotic acids and or polyprotic bases, you're going to obviously have several Ka values that are given to you. The one that starts, the first one that you're given is going to be the most acidic. For example, this pyridoxal phosphate is given in its fully protonated form, as you see right here. The pK1, so that first hydroxy, the pK1, so for that first hydrogen right there, has an acid dissociation constant of 1.4. And then, of course, the pK2 is that other hydrogen right there connected to the phosphate. And that's at 3.44. The third most acidic proton is the other phosphate proton. The second most acidic proton is the one in the hydroxyl group on the benzene ring, and that has a pKa of 3.44. The third most acidic is going to be back to the phosphate group over here, and that's 6.01. And then the last one, the least acidic one, is the one next to the ammonium group, which has a pKa of 8.45. So just realize that all hydrogens on a molecule that are able to come off are not the same. They don't have the same pKa's, right? So you have to know, you just have to recognize that. I'm not expecting you to know which ones are the most acidic or not in this section of our semester. All right, that does it for this video. I'm going to resume with weak acid equilibrium, or section 8.6. See you guys later.